Hello, today I will present our work on predicting crisis in the delivery of emergency care in acute trust using administrative and open source data. Hospitals around the world face increasing demands for both planned and unplanned services. Acute hospital trust in England experienced extreme pressures during winter and were advised to cancel, delay outpatient appointments, and defer non-urgent surgeries. An episode of organizational crisis within an acute trust was defined based on a combination of two performance characteristics for our target and A&E diverts. A 4-hour target is defined as when at least 95% of patients had to be admitted or discharged from A&E within 4 hours from their arrival. This target was selected because it is often used as a barometer for the overall performance of the NHS, is a proxy for inpatient flow, as is highly correlated with inpatient occupancy. While A&E diverts are used only as an action of last resort, and hence shows the trust ability to meet demands. The aim of our study was to examine whether administrative data can be used to identify crises in the delivery of emergency care and to create a predictive model for estimating the probability of such event. Acute trust level daily data were extracted from Hospital Episode Statistics database, and the Winter Daily Situation Reports data were obtained from NHS England. This is the open source data. The study period included 3 winter periods available at the moment of the study. Our outcome was defined as an episode of crisis in the delivery of emergency care in acute trust, which was defined based on two performance characteristics. For our models, we coded outcome as a binary variable. If an episode of crisis in the delivery of emergency care within acute trust occurred at least once during a week, then the variable was coded that trust had an episode of crisis. Otherwise, trust didn't have an episode of crisis. In our study, prediction models estimated the probability of episode of crisis at least once during the following week, Model 1, and fortnight, Model 2. Based on literature review and data available, 17 trust level covariates included in the prediction model. You can see in the table the list of variables and the dataset we were extracted from, and we included various variables like from hospital episode statistic in patients data like number of admissions, the proportions of patients staying in the hospital for more than 7 days, from HES outpatients the total number of outpatients appointments, from HES A&E data total number of A&E attendances, while the rest of A&E related variables were related to type 1 department, which is a consultant-led 24-hour service with full resuscitation facilities and designated accommodation. And winter strip data, which included variables like total number of beds available, occupancy rate, A&E width. Model 1 included covariates from the previous week. In Model 2, covariates from a week 2 weeks prior were included. Each covariate were expressed as an average daily number or proportion per week. We use 3 different methods. So the first one, a mixed effect method, which is an extension of classical statistical procedure, which allow both fixed and random effects and is used where there is the dependence in the data. In our analysis, this dependency of observation within one trust is adjusted by allowing the intercept to vary between trusts. Another method was generalized estimation equation, which is an extension of a generalized linear model and is used to analyze longitudinal and other correlated data, mainly if the outcome is binary. In these models, the dependency of observations within a subject is adjusted by specifying a so-called working correlation structure for repeated measurement of the outcomes. We use autoregressive correlation structure, which was selected by the quality improvement collaborative method. And the final model method was boosted multivariate trace, which is a novel machine learning technique for longitudinal data. It fits a semi-non-parametric marginal model. Unlike the likelihood-based boosting method, it assumes that features are non-parametric, while feature-time interaction are modeled using penalized B-spline with estimated smoothing parameter. To avoid overfitting, the model provides in-sample cross-validation, which can be used to estimate optimal boosting iteration. The whole dataset was used to estimate the risk ratio and C-statistics for the mixed effect and generalized estimation equation methods. To assess the model performance of each model, we use the leave one out cross-validation technique and pool C-statistics. During the study, the median daily number of admissions was 271, of which almost 40% were emergency. Over 94% of daily INEA attendances were at Type 1 departments, of which almost 26% ended in hospital admissions. 49% of TRUS has an episode of crisis at least once, which resulted in 17 episodes of crisis per week during the study period. In the graph, you can see time points of TRUS status in England during pre-winter period. The black dots represent when the TRUS failed, and the grey dots represent when TRUS didn't fail. TRUS who had an episode of crisis on average has a slightly higher number of admissions and INE attendances per day compared with TRUS which did not failed. However, on average, these TRUS were larger one. Furthermore, the daily number of cancelled outpatient appointments and the proportion of INE attendances, which were Type 1, were lower in TRUS who did not have an episode of crisis. In all models, the number of previous INE diverts were the most significant for predicting the episode of crisis in the delivery of emergency care. For each additional period during which there were INE diverts, there is almost 49% for mixed effects and over 77% for generalized estimation equation, increased risk for episode of crisis occurring in the following week. The table represents the model performance. The results present the pool C statistic using leave one out cross-validation technique. We can see that generalized estimate equation and mixed effects models perform similarly, while the boost multivariate trace method outperformed both methods. As every study, our studies will have strength and limitation. The first strength is the use of large national dataset, which covers information related to INE attendances, outpatients, and hospital admissions for all trusts in England. Another strength is use of advanced statistical and machine learning methods. The advantage of generalized estimation equation is the consistent and unbiased estimation of parameter standard errors, while boosted multivariate tree method shown that it could be highly flexible, resistant to overfitting in high dimension. And finally, use of longitudinal data, which provides better understanding of any changes in outcome over time across units and has more power than cross-sectional studies. However, our study have few limitations. First, our definition of outcome is based on two available performance characteristics. Performance characteristics like cancelled, elective, or urgent surgeries were not available on a daily basis. These measures are only published quarterly. However, we believe that 4-hour target is an important measure and can show that trust ability to meet demands. And another limitation is the use of winter sitrep dataset, which provides information about stress only during winter season. So there is no available daily information about number of beds available, occupied, or in either beds during the rest of the year. All food data will be available locally. So the studies are still forward in demonstrating that in principle it is possible to predict future episodes of failure within a trust. If this approach were applied to local real-time data, then it could assist trust in predicting emergency care crises in advance, allowing them to mitigate or even prevent their occurrence. And thank you for listening. If you have any questions or comment on this presentation, please add them as a comment below the video and we will read and respond. Otherwise, contact us by email. Thank you.